Welcome to the office. We want to take a look today at factor groups. We're going to present this first through normal subgroups and then look at it through the kernels of homomorphisms, which of course are normal subgroups. Let's take a look at our notes a moment. So our first theorem is let H be a subgroup of a group G. Okay, pretty straightforward. A group and a subgroup. Left coset multiplication is well defined by the equation AH times BH, right? Coset times coset is equal to AB times H, which is, I would argue that's pretty natural. So we have this idea. Now, you should notice that the implied, or the notation implies multiplication, but we might have addition instead. So this is just a multiplicative representation. All right, so this is well defined if and only if H is indeed a normal subgroup of H. All right. In order for us to prove that, I want us to remember a few different things. Of course, if you don't want to see the proof, then of course, pause this video, stop this video, whatever, move on to the next. I won't know the difference anyway, right? But it's not a bad idea to consider the proof. But it is a long one. So first, I want to make a couple of notes. So for A and B in the group G, and cosets AH and BH for any X and Y. Actually, I want X and AH and Y in BH. We have, if X is in AH, then I actually have that XH is the same as AH. And since Y is in BH, I have YH is the same as BH. Excellent, right? That's just me picking a different representative for the coset group. That's it, right? This is the coset which contains A. Well, if it also contains X, then I can write it as the coset which contains X. Right? That's all that this is saying. All right. So we have this, and to say that coset multiplication is well defined, what do we mean by that, right? What does it mean for coset multiplication is well defined? Means, so if I take AH times BH, throw some parentheses around there, that might look a little bit better. Eventually, I want to say that this is exactly equal to XH times YH. And it might seem relatively obvious because isn't AH equal to XH and BH equal to YH? Why wouldn't they be the same? Well, that's exactly the point. We want to make sure that that assumption, that thing that makes sense, is indeed true, right? That's what we want to verify, or what we need in order to say that it is well defined. So what we're going to do is we're going to implement the definition. We're going to say that AH times BH is AB times H. And then I'm going to do some work that shows that that's equal to XY times H, which I can then, again, implement the definition of this multiplication to show that it is indeed equal to this. All right, because I want this and that to be the same. Doesn't matter whether I use A or X, because AH and XH are the same coset, so I should have the same result. Right? That's what it means to be well defined. If I multiply two numbers, when I multiply those same two numbers, I should still get the same thing. All right, so that's what it means to be well defined. So that's what we're interested in verifying, or right, for a normal subgroup, we're going to assume that We're going to show that that is true, and then we're going to assume that this is true and also show that we must have a normal subgroup. That's sort of the goal here. Part of this is presented in the book, but only one direction. The other direction is left as a homework problem, and I'd like to provide actually all of that proof here. However, there is one other thing I would like to recall. So this has to do with, let's see here, some different representations that we want to consider. Yeah. So this one is a little bit, maybe more of to say it's nuance might be appropriate, but I think that's really making it out to be more than it is. Another thing that I think if we would naturally think this is true, and I just want us to verify that it is. So if H is an element in H, let's see, so a couple of things here. Of course, HH is the same as H. The coset containing H is the coset which contains H because it's in there. Anyway, so a notational thing, but also if A and B are in G, then what I can do is I can consider multiplying on the left by an element. So we have, for example, B coset BH. BH itself is equal to B times H, where H is in H. Okay, so it's a collection of all of these things. If I wanted to, I can take that and I can multiply by A, which seems a little bit crazy, but unsurprising. So this is actually, all right, so this is just a set. So this would be A times K, where K is in BH, but I can represent the things in BH as B times something from H. So this is A times BH, where H is in H. But this is just a multiplication of elements, so now I can apply the associativity in G to get A times B times H, where H, of course, is still an element from H. And then finally, I can recognize that as AB times H. So this particular notational concern is going to become useful to us as we try to work through the proof. But what we really like about that is if one of these elements is in H. I think that's where we're going to use it. So if I have a H times H, this is equal to A times H, and that is equal to, let's see here, that'd be AH. Okay, and it looks like this is what we'll end up using at some point in the proof. So we want to make ourselves aware of that situation. Okay. So H times H is H. If I wanted to multiply two things, I can, all right, take the product on the left by an element of this particular set. Okay. That's what it looks like. All right, so now we can actually start thinking about the proof. All right, so it is a biconditional. It is an if and only if, so we have to prove both directions. So in this proof, we're going to start off with the forward direction, but in either case, we're going to let H be a subgroup of group G. Excellent. So again, this proof is going to have two parts. It's going to have the forward direction, and then it's going to have the reverse direction. In the forward direction, we're going to assume that the coset multiplication is well defined, and we're going to show that the subgroup is in fact normal. Okay. Left coset multiplication is well defined if and only if H is normal. So we assume well defined, and then we show normal. Then we're going to turn it around, assume normal, and show well defined. All right, so we're going to assume coset multiplication is well defined. Now, you might be interested in noting that this is left coset multiplication. Right, not just any coset multiplication, but left coset multiplication. Presumably, it will be well defined for right coset multiplication as well, but that's not what the theorem is actually saying. All right, so assume coset multiplication is well defined. For an element of G, we want to consider the coset AH. Now we want to let X be an element of AH. Since coset multiplication is well defined, we have. All right, so what I'm going to do is I'm choosing some representatives here and also talking about some cosets that really haven't been specified. But what we do have is we have the product of the coset AH and the coset A inverse of H, which may or may not be the same coset. That's not what I'm worried about. If it's well defined, this is going to be A times A inverse times H, which of course is just E, the identity, times H, or just H. And that's fine. But we have this, and we also have that AH times A inverse H. In order for it, if it's well defined, then I can choose any representative, and I can write this as XH times A inverse H, which is, of course, X times A inverse H. So if it's well defined, I can use either representative, and I get the same thing. Therefore, X times A inverse must be an element of H. That is, X times A inverse is equal to H for some H in H. Right? I don't know which element it is, but it is equal to something. And the reason that that is good for us is because I can multiply on the right by A to get rid of the inverse, and I get X is equal to HA. Now, what's the benefit of that? Well, now I've written X as a multiple of H by A on the right, which means X is an element of HA. What good does that do me? Well, I started with X as an element of AH, and then I ended up with X as an element of HA. Thus, I can conclude that things that are in AH also belong in HA, and therefore AH is a subset of HA. AH is a subset of HA. So that gets me half of what I'm trying to show. I want to show that AH is equal to HA, right? They're both sets. So I need to show that one set is a subset of the other in both directions. So now what I want to do is I want to start with something in HA and show that it must be in AH as well. So now let Y be an element of HA. Since multiplication is well defined, let's see here. Oh, actually here. Let's see here. Okay, then Y is equal to H times A. It might be a different H, so I'm going to call it H prime. So let Y be equal to H prime times A for some H prime in H. Fantastic. All right, that's just what it means to be in the set HA. Now, if we consider y times h, I want to eventually show that y is in AH. So I'm working on things from the left here. Now this is equal to h prime a times h, which is equal to h prime h times AH. H prime h, of course, is just h, and this is just times AH. So essentially, this is going away. It looks like what I chose to do here is, looks like maybe I didn't get this order that I was hoping for. H is AH. But that's kind of the same sort of thing that I'm working towards here. H prime H is EH, or just H. Calling it EH is convenient because then I can recognize that this is AH, right? A times E is just A. So now I have YH is equal to AH. If they're the same, then Y must belong in AH. Hence, Y belongs in AH. So I started with Y in HA, found Y is in AH, and HA must be a subset of AH. Fantastic. So I have subset containment this direction. AH is a subset of HA. I have subset containment in the other direction. HA is a subset of AH. Therefore, I must have that AH is equal to HA. That is, H is a normal subgroup. Excellent. So what I've done so far is I have shown that if I have that coset multiplication is well defined, then the subgroup itself must be a normal subgroup. What I also want to show, so I left myself plenty of space here. I'm going to continue on proving the other direction. So now what I would like to assume is that H is a normal subgroup. So I assumed well-defined, I showed normal subgroup. I'm assuming normal subgroup, and I'd like to show that it's well-defined. So assume H is a normal subgroup. Then, of course, just as a reminder, we're saying that GH is equal to HG for all G in G. All right. Let's let A and B be elements of G. And suppose that X is an element of AH and Y is an element of BH. Again, if I want to show well-defined, I want to show that AH times BH is the same as XH times YH. So suppose that X is in here and Y is in there, so that way I can get that thing that I'm looking for. Right, use those different representatives. So since X is in AH, I can say that X may be written as A times H1, and Y can be written as B times H2. A couple different H values there. Excellent. And so I'm going to split my work up a little bit here, so hopefully we're able to follow along easily. But what I'm going to do is I'm going to take XH times YH, and I would like to eventually show that this is the same as AH times BH. The definition, of course, says that this is XY times H. But now what I have is I have this nice way of representing x and y in terms of a and b. So I have x is a times h1, and I have y is b times h2. So I have all of that times h itself. But I have associativity, so I can observe this as a times h1, h2 times b, h. And now what I have, this gets a little bit interesting. Uh, since I have left and right cosets are the same, I can start moving this around, okay? I can move the b onto the other side. So since we have normal, we have h1b, h1, oh, oh, yeah, of course, I wrote those in the wrong order. That doesn't work. I can't rearrange things however I want. A times H, and this is still B here, and this is still H2. There we go. Excellent. So, yeah. Okay, so H2H, I can get to go away, essentially, and then I can rearrange how I like here. Okay, so H1B, this element here, this belongs in H B, which is equal to BH. Hence, there exists an element H3 such that H1B is equal to H3, I'm sorry, B times H3. So since it's an HB and that's the same as BH, I can find this element somewhere over there, in which case I can express it as B times some other H value. So this is equal to A times BH3 times H2 times H. Yep, I wanted that bracket inside of there, didn't I? Okay, that's all right. Rearrange things again. A, B, H3, H2, but H is a group, therefore the product of these two is also an H, and I can call this, if we want it grouped like, so this is where I'm actually implementing what I said on our first page over here. AH times H is the same as A times H times H. So I am implementing that now. This is going to allow us to write this as AB times H3, H2, H, which is just A, B, H. Wonderful, because now I can recognize this as AH times BH. Ah, so I have that XH times YH is equal to AH times BH. Yay! Right through a collection of definitions of how our left coset multiplication right is defined, as well as observing what it looks like to have elements inside of a set or coset rather. So this looks good. This looks good. Thus, coset multiplication is indeed well defined. So I have proven it the forward direction, I have proven it the backwards direction, and now I would like to draw my conclusion. Therefore, coset multiplication is well defined if and only if H is a normal subgroup of G. Awesome. A little bit lengthy, so thank you for your time and your attention. But that's what we wanted to show, right? So feel free to review the beginning of the video to capture, again, what that theorem was actually stating, which, of course, we said at the end of our proof here. But anyway, I'll see you back in the office for more theorems, definitions, examples.